All right, so hi, my name is Gints. I work here at Gravity team, and I'm going to be talking to you today about the basics of speed on modern hardware. I promised to give you a glimpse into the mindset of the techniques for writing efficient software here at Gravity team, into the mindset and techniques that are essential for building performance software. So let's just look at some of the definitions so we're clear on everything. By modern hardware, I mean anything basically within the last 10 to 15 years, whether it's your run-of-the-mill desktop server CPU or a server CPU or a mobile device. Everything I'm going to say is going to apply to most of them. And what I'm going to say has been pretty much true for the last 10 to 15 years, and I predict that it's going to be true for many years to come. So this is not something that changes every couple of weeks. This might be something you actually want to learn. Yeah, I'm going to give you a glimpse, which is I have to do the talk today in 40 minutes. There's a lot to say. We're going to do a bit of a speed run. I'm going to try to keep it short, but give you some useful information at the same time. By efficient, I mean something that's working in a way that does not waste a resource. Today, our resource is going to be time. We're going to be interested in doing things fast, but I'm going to spend about half of the presentation trying to convince you that to save time, you need to be mostly mindful of how you use space. What do I mean by here at Gravity? For obvious reasons, we're not going to be looking at any production code of Gravity team today, but basically everything has been taken from one or other internal talk where we've discussed similar subjects. So this type of thinking is something we do use here for the parts of the code where it should be used, not everywhere. And also, I just like the definition of the word performant. It doesn't mean actually good performance. It means functioning as expected mostly. So I think it's a nice lens to look at everything I'm going to say today. The next time you write some code and it doesn't maybe do what you expected it to do, I'm going to give you a quick short list of what to think about. So maybe that'll help you improve stuff. And also, the sum of the first k odd integers is k squared. I mean, that's true, but irrelevant, okay? So some things we're not going to be talking about today is going to be databases, networking, your cloud infrastructure, microservices, anything like that. There's a lot of topics where performance might be important. We're just going to be ignoring them today. I'm going to be talking about one topic only, writing efficient code on a single machine. Which means we're going to be in the situation of no helping calls to a database or an external service. We just have our CPU and we need to do stuff fast on it. Most of the stuff I'm going to be talking about today is stuff that Big O doesn't want you to know about. Literally, Big O just throws this all out and says those are just constant factors, but we're going to be interested in those constant factors today. Also, I'm going to be mostly talking about integers, but of course, keep in mind, if you work in games and you see me incrementing or iterating a bunch of integers, think of iterating maybe a couple of entities in your game and doing something with them and so on. Like, I'm going to keep the example simple, but they do scale to larger things. Do's and don'ts for today. Do ask short questions in line. If something's not clear, let me know. Do keep the longer questions for QA at the end. We only have 40 minutes and I'm going to have to speedrun this. And do participate. Most of the slides are going to be some code and I'm going to be asking what you think is going to happen. And it will be more fun if you try and guess out loud. And also the sum of the first k odd integers is k squared. Yes, but I don't know what that has to do with anything. All right. Now, this is the stable stakes. This is the prerequisites. You got to know this. And I'm sure most of you do. I'm sure all of you do. This is how your CPU is kind of laid out. You have your CPUs, which have some L1 data and instruction caches. You have your L2 caches, which may be inside or outside the CPUs. Multiple cores may share the same L2 cache. Sometimes they are, well, mostly they are. Each core gets a separate one, but sometimes they are shared. Then you have the L3 cache, of which there may be one or maybe multiple caches somehow split up between all the CPUs you have. And after that, you have your main memory. And accessing them gets costlier the further away from the CPU itself you go. So the L1 caches are going to be 1 to 3 cycles, L2 caches somewhere like 4 to 12, maybe 5 to 20 on some models. L3 is going to be about twice as slow as that, and then the RAM gets really slow. So don't really pay attention to the exact numbers here. Just have the general picture in your mind that you have your caches. They get larger and slower the further away you go from the CPU. All right, everybody with me so far? All right, let's look at the first example. We're going to record the current time. We're going to sleep for 1 second. We're going to record the time, and we're going to print the difference in times. What is this going to print? At least one of you has to have a guess. It's going to print 1 second.
1 second, yeah.
This was a test if you guys are asleep. It seems you are asleep. All right, let's wake up. Yes, unsurprisingly, this prints out 1 second. So please, if you this is how the whole presentation is going to work. I'm going to have some code. I'm going to ask you what happens. It will be more fun if you try and guess. Also, for each example, I'm going to have a link where after the presentation you can go and play around with stuff and make sure I'm not lying to you. And yeah, that's it for the warm-up example. All right, let's try a real one. So we're gonna have a huge two-dimensional array, 5,000 by 5,000 integers. Each integer is 4 bytes, so this is 100 megabytes. There's no way this fits inside any of our caches. This will leak into the main memory. And we're going to iterate over all of these integers and just calculate the sum. And we're going to do it two different ways. On the left, the outer loop will be the first index and the inner loop will be the second index. And on the right, we'll swap them around. So the outer loop is the inner index and the inner loop is the outer index. And the question is, these obviously do the same thing. They're going to give us the same result. Is there going to be any performance difference here?
Yes. Yes.
All right. Why?
It depends how it's stored on a disk in the rows or the.
But this is not in this. This is in main memory. This is in RAM.
It's row.
Yeah.
It will be cache misses or
cache misses all around. Okay. And so you're saying the version on the left is going to be.
On the left will be fine, and on the right should be cache misses.
Okay. Yeah. Exactly. So the version on the left is about 35 times faster, and it's because of cache prefetching. So this array is way too big to fit inside any of our caches. So every time you ask for some integer, that's going to be something you haven't used in a while. And so it would result in a cache miss, exactly as you said. But the important takeaway is that modern CPUs have this thing called prefetcher. And what it does is every time you want to look at something in memory, it tries to predict what the next thing you're going to look at is going to be and tries to prepare that for you ahead of time. So in the scenario on the left, we're basically iterating through the memory in a sequential manner. So the prefetcher learns that really fast. It knows that if I'm reading here, I'm just going to need the next piece of memory right after that, and it's going to prepare that for you, and as soon as you need it, you're going to have it. And on the right, the prefetcher will not be able to do this, and you're going to be paying the full cost of fetching from main memory potentially every time you access something. So, all right, let's add some more numbers. So now the opposite example, we're just going to have a really small array of 512 elements. Each element is going to be a struct with 2 integers. And on the left, we're going to go through the struct in a sequential manner, and we're going to count up all the integer A sums. On the right, we're going to do the same thing, but we're going to count the integers A separately and the integers B separately. So in some sense, we're doing twice the useful work on the right. Question is one going to be faster? Are they going to be the same? If one is going to be slower, is it going to be twice as slow because we're doing twice the work? Is it maybe going to be 50% slower because here on the left, we're like doing 1 integer addition, but we're also incrementing the index. So maybe here we're doing 2 additions, here we're doing 3. So maybe we expect it to be 50% slower.
Same?
Almost the same. Yeah, exactly, almost the same. In this case, we get twice the work done and with only 10% time difference. And the key non-differentiator in this case is CPU instruction level parallelism. So the key takeaway is that your CPU has multiple integer arithmetic execution units. In this case, mine has at least 2. And I am able to basically add 2 integers at the same time, totally separately from each other. They don't slow each other down in any way. Okay? Okay, let's add some more numbers. Whoops, gave it away. All right, a huge array again, 1,000,000 elements, and this time each element is going to be on the left side a struct that contains 8 integers, and on the right side we have 8 arrays, each containing 1 of the integers, and we're just going to be summing up the sum of all the A's. On both sides, we're going to be walking through the memory sequentially. And yeah, what's going to happen here? Any guesses? Like, they perform the same as a good guess, maybe? I don't know.
Left part is faster. Slow.
No.
This part is faster with the struct.
Say second. I think second will be faster. Second.
Okay.
Right one.
Who said second? Maybe let's have a vote. Who said first? Okay. Who said the same? Okay. So I did give away the answer. The one on the right is gonna be faster, but yeah, it might be interesting to understand why. Anybody who guessed the one on the right is gonna be faster? Yeah.
I think it will be on the stack. So these values will be on the stack, and therefore.
Let's say this is heap allocation. I have it as a struct here. If it was a vector, it's the same thing.
It's because of the layouts of the structure. So the one on the left side means that essentially all of the variables are kind of right next to each other.
Yeah.
Whereas the one on the right side means that you have large arrays with kind of predefined data sizes. So your CPU can easily just jump in chunks like that.
Well, I want to say this: we can jump between them with the same ease, as in, I mean, the offsets are going to be smaller.
Yeah, but the thing is that your CPU needs to read in the whole structure to operate on it, right? Yeah. Whereas on the right side, you don't have to do that.
You're on the right track. I have a problem with your wording, but you're on the right track.
Maybe because we have pointer to the structure, so we need to jump to pointer.
No. That will be a non-issue. Okay, I will give the points to you. You are the closest to the answer. So framing it as we have to read the whole struct is maybe not the correct answer, but you are very close. So this is about useful data density per cache line. So the key takeaway is the base unit of interaction of the CPU with the memory is a cache line. every time you read something, whether you like it or not, you're going to read a whole cache line. Every time you write something, you're going to write a whole cache line. The second part is not strictly true, but let's say it is. So here, what we are doing is basically every time we load the cache line, we are using 1/8 of it, right? We are using 12%. And then for the next edition, we're going to have to load the new cache line. Here, our integers are sort of densely packed. So every time we read a cache line, there's actually 8 useful integers in there, right? So think about this as reading and writing to memory is like sending a package by mail that has a fixed size, and you pay $10 for it. Every time you send it, you pay $10. In our case, we pay with time. Whether you use like 12% of it efficiently, or you use 50%, or you use all of it, you're still paying $10. And here we are being bottlenecked by the mailman, by the prefetcher, because this is all like prefetched very nicely. It's just that the speed at which we can prefetch is insufficient to give us a whole cache line for each edition. Yeah, does that make sense? Is everybody on the same page? Okay. All right. Let's see how we're doing for time. Yeah. Okay. All right. Next one. Okay, adding and multiplying numbers. So we're going to have a relatively huge array, although the size doesn't really matter that much this time. They're all going to be integers again, random integers in the range 0 to 1000, just distributed randomly. And we're going to loop through all of them. If the integer is higher than 500, we're going to add it to some counter. And if it's lower than 500, we're going to multiply it, multiply some counter by it. And the two things we're going to be doing is keeping the buffer in the random order, so each integer has the potential to be of any value, or before we do the benchmark, this is not part of the benchmark itself, we sort the buffer. Second one is going to be faster, because?
Because of branch prediction.
Branch prediction, exactly. So, the second version is about 5.5 times faster. As the gentleman over there said, this is because of cache prediction, branch prediction. So the key takeaway is when your CPU executes an instruction, it doesn't just do it in one cycle or something. It takes a lot of cycles. There's a pipeline in modern CPUs, and let's say when you need to do something, the first step of the pipeline might be for the CPU to decode the instruction and just understand if it's a valid instruction at all. The second step might be figuring out what the inputs are, what the outputs are, where to get them, and so on. Then the third step might be to, remember I told you there's multiple execution units, it might be to schedule this instruction for execution on one of them, and there's a bunch of stuff it wants to do. In other words, the time from when an instruction sort of starts to get executed to when it's done, it's not one cycle or anything, even if you kind of look at the spec and see that, okay, integer addition takes one cycle. It takes longer in the pipeline. And sort of a natural side effect of this is that, and of course, while some instruction is, let's say, stage 2 of the pipeline, some other instruction is already getting loaded into stage 1 of the pipeline. And so a natural side effect is that anytime you have a branch in your code, let's say an if statement or a virtual function call or something, the CPU kind of has to guess what the next instruction is going to be. Are we going to multiply or add in this example? And it sort of continues working with the pipeline as if that's what we're going to do. And then once it progresses far enough into the pipeline, the CPU might understand that, oh, actually, we made a wrong guess. Now we have to undo all of the things in the pipeline since that point and restart our work on the second branch. So yeah, and this can obviously be costly. So 5.5 times in this example.
You have to pay a lot for sorting.
Yes, but I'm trying to just illustrate the point about how a branch predictor is going to behave. Like, oh yeah, and the reason why the second, the sorted version actually works faster is because now, anytime the CPU hits that branch, the branch predictor says, okay, the last 10 times we were here, we did this thing. Let's guess that we're going to do the same thing again. And so basically, for the first half of the array, we only take one branch, and we hopefully hit none or a small number of branch mispredictions. And then once we switch over into the second half of the buffer, we're gonna always take the other branch, and that's gonna be easy to predict as well. So we're not gonna be like throwing away all the work in the pipeline and restarting it over. Okay, is that clear? All right. Okay, let's count to 1 billion. So we're going to have some number of threads. That's going to be the parameter we change, how many threads we use. And we're going to have a small array, well, exactly the same number, sized exactly as the number of threads that we're going to have. So each thread is going to take one element from an array. And that array is going to be an atomic integer, and we're just going to increment it 1 billion times in each thread. And we're going to, again, do it 2 ways. On the left, well, let's start with the right side. On the right, each of those integers is just going to be a regular 8-byte atomic integer. So the array is, again, going to be densely packed. And let's say we expect all of them to be in the same cache line. And on the left, we're going to ask the compiler to place each of those atomics inside a unique cache line. So it's x86. I asked for the alignment to be 64 bytes. Right? Everybody understand what's happening?
And so the question is, what will be faster, aligned version or not?
That, and also what happens with each of them as we increase the number of threads. So each thread gets a unique integer that it's going to increment. The difference is whether all threads store their integers in the same cache line or on separate cache lines. And yeah, left versus right, and what happens as we increase the number of threads from 0 to 8, let's say, 1 to 8.
So the aligned version will be faster.
Yeah.
And I think the threads should be spread across the cores, so it will be in parallel execution.
Okay.
I assume this will be the same.
The same.
Because
Okay.
it's atomic action. And,
Yeah.
The first one will be the faster.
Okay, why?
It's hard to argue.
Okay. Okay. All 3 versions represented. Nice. Okay. All 3 versions represent. Okay, so let's first have a look at what the aligned version does as we increase the number of threads. So actually, the thing that I can't explain is why there is a difference between 1 and 2 threads, but the rest of it is like we keep adding threads, nothing changes. All of them complete their work in the same time, and they're obviously executing like independent pieces of work fully independently. They don't like mess with each other in any way. Okay, on the right side, we're going to have a different story. As probably expected, we're going to have, as long as we have just one thread that gets one atomic, it stays exactly the same. Okay, and then the second atomic costs twice as much as the first one did. The third one adds So the first one cost 4 seconds, the second about 9.5, then about 6, then 14, then 13, then like 17-ish. It's bad. It's bad. So why is it bad? And why is it good on the left side? Any guesses? I think you had a...
Because of alignment.
Yeah, but so why?
Because the CPU, so it's convenient for CPU to basically use instructions which are aligned. Because of the cache lines.
Are not aligned in any way. This is the data structure is aligned. The instructions are not being aligned.
Data structure.
Yeah.
So it's like for the cache lines, I think.
Okay.
Because the CPU has to lock the cache lines somehow.
Exactly. So the fundamental unit of interaction between CPU and memory is a cache line. I said that before, right? And so here, as we do atomic reads and writes or increments, the CPU needs to lock access to that variable so that it knows that when it's tried to read, add 1 and write back, nobody else did so at the same time. So you can think of it as a lock implemented in hardware. So this is one x86 instruction. It's just that physically somewhere there is essentially a lock where all the CPUs negotiate like who has unique exclusive access to a particular cache line. And the granularity of this negotiation is a cache line. So what happens is that on the left, every thread, every core that executes the thread gets to just say, yep, that's my cache line, increment by 1. Yep, that's my cache line, increment by 1. And there's never any problems. There's nobody else trying to say that it's their cache line. On the right, all the things are in a single cache line, so every thread always waits on every other thread, and there's some kind of a mess going on there I don't want to get into. So this is called fault sharing. It's when logically independent pieces of work happen to become dependent on each other just because the data happens to be in the same cache line. As a rule of thumb, as long as you have a bunch of threads only reading from the same cache line, everything is fine. As long as you have a bunch of threads only writing to the same cache line, it's also fine. Again, not strictly true, but let's say. And if you have a bunch of threads reading and writing from the same cache line, you're going to run into problems. And especially if you do atomic operations, reading and writing from the same cache line, you're going to run into problems. And the solution is to not have things be on the same cache line. Okay, let's use a bunch of data. Let's zoom in. On the right here, we're going to have a huge or not so huge values array. Each element is going to be an integer. We're just going to loop through all the indexes, and we're going to increment each of those integers in the array. And we're going to count how many increments we did, and we're going to see how many we managed to do in a second. This shuffle thingy is this function here. Don't read into it. Just trust me when I say it maps all the indexes to a somehow otherwise arranged index, so that we still go through all of the indexes 0 to n. We just do it in a different order. And the order is random enough that the prefetcher basically becomes ineffective. Okay? So some array, which we're going to increase in size and see what happens. And we're randomly accessing elements in it and incrementing by 1. So let me just give you the first result. Oh yeah, and think of the values we're changing, not in terms of how many integers there are, but in how many bytes they take up. So in this case, each integer is 8 bytes. So if we have 16K working set size, that means there were 2K integers. But we're just interested in the size of our working set, because that's what the sort of the memory system is gonna try and provide us the bytes to work with, right? So what we see is, while we keep the total working set size pretty low, we're able to do quite a bit of additions. In this case, 4.5 billion per second, so more than one, let's say 1.5 per cycle. So that's pretty good. For those of you who can see, you can notice that as we get closer to 65K working set size, we decrease quite significantly the number of ads per second we're able to do. Anybody want to take a guess as to what my L1 cache size is? It's right between these two numbers. It's 48K, so 32K is still fully within L1 cache. We're accessing things randomly, but they're right there in L1 cache, and so everything's great. And as we start to sometimes have to dip into L2, we get a bit slower, as expected, right? Now, the L2 size on this machine is 1 megabyte. So here, as we increase the working set size, the probability that the next read is going to have to go into L2, not 1, increases, and our ads per second decrease accordingly, as expected. And by the time we're fully using all of L2, we've become about twice as slow. Right? Makes sense. As we dip into L3, we become even slower. And then the L3 cache on this machine is 12 megabytes. So when I show you the results for 16 megabytes, what do you think is going to happen? You have a guess. I'm sure you have a guess. It's going to get much slower, right? These were the 3 cache levels. And now once we go above a working set of 8 megabytes, there's going to be some probability that the next read has to come from main memory and not from some cache, right? And it's going to drop down significantly. So here, while we were still in the caches, we dropped from about 4.5 billion to 1.5 billion. And as soon as we went into main memory, we're just like a 6x drop to about 300 million. And as we grow our working set to about 16 gigabytes, we drop down to about 47 million ads per second, which is roughly 100 times. So 80-ish, 90-ish times slower. Right? So anybody want to explain how that happens? What would be the, yeah?
Because basically we're using the, I don't know, SSD or something like that.
No, we're not. This is all still in memory. This is just about going to memory. So I'm going to say the key differentiator here is the probability of data being in L1, L2, or L3. The further out you get, the slower it gets. Once you get into main memory, if you're doing random accesses, it's going to be bad. Okay, let's do the same thing. Except this time we're not going to shuffle. Forget that magic function. It's just if we give it an index, it gives us back the same index. So we iterate the values just sequentially. And I'm going to give you the first 3 results. Basically, the first thing you'll notice is that we can do almost 3 times more additions per second. But this is not because of the memory access pattern. This is just because previously we had some multiplies here and some other stuff, and now we just increment an integer. So the operation we do on each integer just became a lot faster. So previously we were blocked by the CPU actually doing the additions. Now we are not. This is just how much data the L1 cache can feed to us. And so let's remember, we're doing this in a sequential manner. So the prefetcher is going to predict the next data that we need very, very nicely. So anybody want to guess what happens once we start reaching into L2?
Down. But not as much.
It will slow down, but not as much. Okay, that's a good guess. In this case, it didn't slow down at all, basically. So as long as we are accessing the memory sequentially, even if we start to mostly go to L2, the prefetcher is able to fetch the data fast enough for us not to notice a difference. The same actually happens for L3, maybe a little bit degraded, going from about 12.5 billion to 11.5 billion per second. And then once we start reaching into main memory, any guesses? It becomes fast somehow. No, it becomes slow, of course, but how slow? Is it going to be like this slow? Is it going to be 80 times slower? Not dramatically, exactly. So we bottom out at about 3.5 billion ads per second, which is to say, if you're accessing memory sequentially, even when you have to go to main memory for every read, it's still just some small number of times slower than working in L1 all the time. Okay? And the key differentiator here, the key non-differentiator here, the one which keeps the numbers flat, is the prefetcher again. All right, one last time using a bunch of data. This time we access the memory sequentially, but we significantly increase the work that we do for each integer. Previously, there was just an add. Now there is some calculation. It doesn't matter what it is. It's just a bit longer to calculate than just adding one. So we see that this is the speed we get while working in L1 cache. Anybody want to predict what happens in L2?
The same.
Pretty much the same. L3?
The same.
Pretty much the same. And main memory?
The same.
Exactly. Exactly. So there's a bit of degradation, but let's not count that. So the key takeaway, I guess, is even if your working set is huge and you're accessing it sequentially, as long as the operation you're actually doing on each cache line is big enough, I'm sorry, the prefetcher is likely to hide all the memory stuff from you, and you're not going to see any performance degradation. Okay, key takeaways. You are likely bottlenecked by memory access, not CPU, unless you have already thought about some of the stuff I've mentioned. I feel strongly this is true for your average program. It just is. The probability of data being in L1, L2, L3 matters a lot. If you can't fit your whole working set inside the caches, then the parts that you are accessing outside the caches, make sure you're accessing them sequentially or in some other way that the prefetcher can predict, and that's going to be good for you. And the unit of interaction between CPU and memory is the cache line. Okay. Okay. As far as branch prediction goes, you are likely slowed down. I didn't use quite as strong of a phrasing here, by unpredictable program flow, not actual instruction execution. Meaning these branch mispredictions. Remember the example about adding and multiplying. They are an issue, but they are probably less of an issue than memory accesses in the average program. Yeah, you want to make sure you don't interrupt your instruction pipeline. And if you have some code that just has to have branches, think about whether or not you can feed the data to it in a way where the branches are still there, but the branch predictor at least can do a good job of predicting which branch you're going to take. And you can sometimes get free stuff. Remember the example about instruction level parallelism. We literally counted 2 sums instead of 1, and we only paid 10%. Sometimes you're not even going to pay 10%. All right, we're pretty much out of time. I'm going to try to do the rest of the stuff in 5 minutes, so let's speed run. Couple of points about modern compilers. Here we have a struct. It has 3 integer members. It has a heap allocated vector member. It has a constructor, which takes in some arguments, does a bit of math, stores in the internal integers, and also does a heap allocation on the vector. And the struct also has a getZ function, which just returns the Z member of that struct. And we have this function, totally separate from the struct. What it does is it creates a new struct with the parameters 1, 2, 3, and it returns whatever value getZ returns. The question is, what's the assembly for this function gonna look like? I don't need like exact instructions, just give me the general idea.
Constant.
Sorry?
Return some constant because it can be pre-calculated.
Who's saying that? I'm sorry, I'm blind or something? Oh, yeah, exactly. It returns a constant because it can be pre-calculated. So, good guy compiler, what it did for you? Totally threw out the heap allocation, no need for that. Totally threw out these two variables. You don't use them. And this variable that you use, it knows that A is 1, B is 2, and C is 3. So the result is just 1, 2, 3. And it just returns that. Nice. But the key takeaway I want you to notice is that all of these nice things that it did for you, it could only do because it was able to inline these two functions, right? If it was not able to inline these two functions, it would have to just call the constructor without knowing how it's going to get used, would have to do all of this. And the same for the getZ function. So the key to getting all of this nice stuff was inlining. Okay, everybody on the same page?
Question.
Yeah.
So can you write shitty code knowing that compiler will fix you?
If you know the compiler will fix you, then yes. But that's one of the takeaways. Learn what the compiler can and cannot do for you. So let's look at another neat trick the compiler will do for you. A function takes a parameter, an integer, and sums up all the integers 1 through n and returns the sum. What's the assembly going to be? Okay, so we all know that the sum of the integers, 1 through n, not the odd ones this time, is n times n plus 1 divided by 2, yes? So basically, we know that this sum is somehow you can calculate it just knowing the n without doing the loop. And that's exactly what the compiler does. Let's not dive into the assembly. Just notice there are no conditions here, there are no jumps. So it took this loop and turned an ON algorithm into an O1 algorithm. It replaced all the sums with a single multiplication. And then there's a division, which it turned into a byte shift, doesn't matter. That's what it did for you. And then, of course, if I ask you what the assembly for this function is going to be, you're all going to say a constant. It doesn't even need to do that. It just inlines it, pre-calculates a constant. All right, this one we'll skip. It's not that important. Key takeaways: let your compiler inline. If you let it inline enough, it's going to apply an infinite bag of tricks on your code and make it better. Don't forget, there are things the compiler cannot do for you. Remember the cache line trick with the atomics. The compiler it's not that it can't detect it. Even if it was able to detect it, it's just not allowed to do this optimization. Remember the struct of 8 elements versus the array of a struct which has 8 elements versus 8 arrays which each just have 1 element. The compiler is just not allowed to do that for you. So learn how the compiler works, what it does, and take care of the things that it cannot do, and it will do the rest for you pretty well. Let's skip this. Yeah. Let your compiler inline. All right. I think. All right. Speedrun. Last example. Speedrun. We have 1 minute. Let's do it. So this is a little bit about interacting with the kernel. An example of using blocking sockets. So we're going to have a server, we're going to have a client. The server just reads 8 bytes from a socket and writes it back. The client just it sleeps for a second and then it takes the timestamp, writes 8 bytes to the server, reads it back, and records the timestamp and says how many nanoseconds did the ping take. So both of these threads are going to be in the same process on an AWS like C7i machine, let's say. And the question is, how long does it take for a ping between two threads using, let's say, the loopback TCP interface?
Couple of milliseconds.
Couple of milliseconds. Could be. Any other guesses? It's about 0.3 milliseconds, so about 350 microseconds. Again, you're going to say, Gints, you're an idiot. Why are you using a TCP socket to talk between two threads of the same process? This is stupid. Okay, let's use crossbeam channels. We're going to move to Rust now. So crossbeam is a popular inter-thread communication library. We're going to do basically the same thing. We're going to receive on the server, we're going to receive and then send back. And then on the client, we're going to send and see how long it takes for us to get the response without doing the TCP nonsense for some reason. Any guesses?
1 second.
Sorry?
1 second.
1 second. Okay, that's a bit pessimistic. Yeah, okay.
Higher.
Sorry?
The time will be slower.
Will be slower than going through TCP.
Yes.
I think it's going to be very similar.
Very similar. Okay, why?
Because at the end, it's a syscall in both cases. Right?
Okay.
So in one case, you write to the socket, it's a syscall, then you read, it's another syscall.
Yeah.
In this case, when you communicate between threads.
Yeah. There is going to be a syscall in terms that there's going to be sort of an event that gets triggered to wake up the receiving thread.
Yeah.
Yes. And so you're saying the same, roughly.
Just a guess.
Yeah, that's a very good guess. So it is a bit faster, but the bulk of it is the same. And that's because the bulk of this delay has nothing to do with actually passing the data around. This is just about the kernel waking up threads so that they process 1 byte and then go back to sleep. Key takeaway, don't rely on the kernel to wake you up in a timely manner. So what can we do? What if we do this? We just have one atomic integer. The server is just gonna wait until somebody puts something other than 0 in that integer and immediately put a 0 back. And the client is going to just put a 1 there and see how long it takes for the server to put a 0 back. So again, a kind of a ping between the client and the server. Any guesses?
10 micros.
10 micros, okay. So we had 300 microseconds, now we are guessing 10 microseconds, okay? Anybody else?
I think it's going to be faster because in both cases, it's just a thread blocking and reading the same variable all over again. So it's just a matter of the instructions
It's
being
not
loaded.
even blocking, right? That's the thing, it's a tight loop. We are using the whole thread, but we're not blocking, we're not going to sleep.
It's just spamming
Learning it.
Yeah, we are burning it, exactly. And so the result is about 250 nanoseconds, let's say. It's actually a bit faster, but anyway. So, what can we take away from this short look at interaction with the kernel? Avoid going through the kernel if you can. If you do use the kernel or you use some libraries which use the kernel transparently to you, make sure you measure the overhead and decide if it's worth it to you. You are probably paying more than you think for some operations, but again, take into account, it's not like the people writing the kernels are idiots or the people writing the crossbeam channel library are idiots. It's just that they have a different set of requirements. And you should evaluate how well those match up against your requirements, and maybe some flexibility that they offer is not needed for you, and then why pay for it? Use only what you need, pay only for what you use. In where it matters, don't try to eliminate every kernel call everywhere, right? All right, that's it for today. Almost made it on time. Thank you guys.